Have you heard of free radicals? Anybody? Are free radicals good for you? No, they're not good for you. A free radical is a molecule or an ion that has an odd number of electrons. So you can't possibly draw a Lewis structure that obeys the octet rule. These species tend to be unstable. They react in a way that is not always desirable. Free radicals in your body can cause problems. Nitrogen monoxide, we'll see, is a free radical, and that is a common source of pollution. So even though Lewis theory predicts these are unstable, they do exist, but they are reactive. So let's draw the Lewis structure for no. So there's nitrogen and oxygen, and there's got to be at least a bond in between. The nitrogen has 5 valence electrons, the oxygen has 6, got 11 electrons. You can tell right away there's a problem, because Lewis structures are all about pairs. This is 11. And we can't do a double thing where we do 2 nitrogens and 2 oxygens. We got to stick with the formula. So what we're going to do is we're just going to do the best we can. So there we've got 2 in the middle, 4, 6, 8, 10, 11, right? So this nitrogen has 2, 4, 6, 7. The oxygen has 2, 4, 6. I think we can do better than that. How about if we take this pair of electrons and share it? You can't share the lone electron. So I'm going to take a pair from the nitrogen and share with the oxygen. 2, 4, 6, 8, 10, 11. So now this oxygen, 2, 4, 6, 8, the nitrogen has 7. So we could do it that way, or we could give oxygen that lone electron, right? Yes? Yeah, formal charge is going to come into play here. So we could draw 2 of these, and we're trying to decide which one's better. Let me get this out of the way. So we're going to look at the formal charges. So up here, again, we're cutting the bonds in half. Nitrogen brings 5 electrons to the molecule, valence electrons, and here it would leave with 1, 2, 3, 4, 5. 5 minus 5, so that one's 0. And here the oxygen brings 6 and leaves with 2, 4, 5, 6. So that one's 0. So I think we have our winner there, right? 0 formal charges. Let's just check this other one though. So cutting this in half, nitrogen bringing 5, leaving with 1, 2, 3, 4, 5, 6. So that would be -1. The oxygen bringing 5, leaving with, bringing 6, leaving with 5 would be +1. So our winner is this one. So we just do the best we can, minimize the formal charges, and that's all we can do. These molecules and ions violate the octet rule. We can also violate the octet rule by not having 8 electrons and being okay with it. So hydrogen does this all the time, but hydrogen has its own rule, right? The duet rule. There are some other elements, though, that just kind of play by their own rules. And these tend to be the smaller ones, like boron. Boron tends to form compounds in which it only has 6 valence electrons. So let's look at boron trifluoride and see what happens. So put boron in the middle, and the fluorines around it. This is going with symmetry and with more electronegative on the outside. So number of electrons, how many valence electrons does boron have? 3. And fluorine has 7, and there's 3 of them. 3 times 7, 21, plus 3, 24. So we got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. What we've been doing in a case like this is we take one of these lone pairs and we share and make a double bond. What are the formal charges right now, though? All zeros. Because boron had 3 valence electrons, and if we cut these bonds in half, it's going to leave with 3 electrons. That has a 0 formal charge. Fluorine brought in 7, it's going to leave with 7. Everything's 0. If we obey the octet rule by giving us a double bond there, now we've got formal charge. The boron is going to be -1 and the fluorine is going to be +1. That's not good. Now, BF3 does tend to react in a way that completes the octet on boron. But this boron trifluoride with single bonds that's a good molecule. That's actually what it is. Beryllium is another one that tends to have incomplete octets. And then we have the opposite, which is expanded octets, having more. So you can only do this for elements in period 3 and above. So let's draw Lewis structures for arsenic pentafluoride and sulfur hexafluoride. So arsenic pentafluoride, so arsenic in the middle, and 5 fluorines, so there's 4 of them, and we'll stick 1 in there. Valence electrons, arsenic has 5. Arsenic has 5. AS, 5. And then we've got 4 times 7, it's 28. No, we've got 5 times 7. So this is not a free radical. Yeah, 40. Whew, that's scary. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. All very nice, except arsenic has 10 electrons, not 8.
7 times 5 is 35.
Plus 5.
Oh, plus that.
Yeah. So the arsenic has 10. But what do formal charges tell us? It's all zeros. Arsenic had 5 valence electrons. If we cut all these bonds, it's going to leave with 5 electrons. It comes out even. And the fluorines are always going to be, if you've got 1 bond, they're zeros. Let's do sulfur hexafluoride. Sulfur in the middle. There's 4. We just kind of have to squeeze the other 2 in. So we've got 6 from the sulfur, and we've got 6 times 7, 42, 48. I'm going to make that a little smaller. These aren't fitting very well. You can count. These are stable compounds. So here we've got sulfur, 6 fluorines, and the correct number of valence electrons, and 0 formal charges. The only thing wrong with this is that the sulfur has 12 electrons around it instead of 8. So how does this even happen? Yeah, these things might be on the exam. Not the one today, thank goodness. Right. The reason this can happen is because elements in period 3 have their 8 valence electrons would be in the 3s and the 3p, but there's also 3d orbitals sitting there, right? So in the hotel, on the 3rd floor, there's the S room and the P room. There's also an empty D room. So if we've got 10 electrons here, the first 8 will fill up the S and the P, and then we can stick those extra 2 in that empty D room, and it's okay. Oxygen can't do that. Nitrogen can't do that, because the second period, the second floor in the hotel, only has the 2 rooms. Once you fill up with 8, you're done. You can't fit any more. The d orbitals are only a little bit higher in energy than the p, and so they can take those extra electrons.
That's for elements that have 4p.
It's for elements that have, well, yeah, it would have 4p. Yeah. Well, sulfur, no, it's elements that are in the 3rd period. So 3s, 3p, they have access to the 3d. They don't actually have electrons in there, but they have access to it. Just like, if a hotel, if there's nobody staying on the top floor, that doesn't mean the rooms don't exist. They're there. There's just nobody in them. So the 3rd floor, like for sulfur, that d orbital, those d orbitals are empty, but they're there. And if sulfur needs to bond and form 6 bonds, it can put the extra 4 electrons in the D subshell. Okay? Any other questions? You can even do 14 electrons. So let's look at sulfuric acid. So we're going to put sulfur in the middle and the oxygens around it. And then the hydrogens are actually going to be on the oxygens. I wouldn't necessarily expect you to know that at this point. These hydrogens being on the outside, those are the hydrogens that get lost when this ionizes and forms an ion. Counting up electrons, there's 2 hydrogens, and there's a sulfur, and 4 oxygens. So that's what, 32? No, 24, 30, yeah, 32. So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Yay! Right? Octet rule, awesome, move on. No, what are the formal charges? They are not all 0, right? The sulfur brought 6 electrons, and how many would it leave with? 4, right? It's going to have 1 here, here, and here. So that's a +2 on the sulfur. This oxygen has 2 bonds. That oxygen has 2 bonds. Those are going to be 0, but this one's not 0. That oxygen has a -1 formal charge, and the other oxygen has a -1 formal charge. Sulfur's in period 3. We should explore whether expanding the octet can reduce the formal charges. A negative formal charge means that this guy has maybe too many electrons. Positive formal charge means this guy doesn't really have enough. So this guy with more, we want to do some sharing with the sulfur. We don't want to just put these electrons on the sulfur, because then the oxygen won't have an octet, and that's bad. But let's just take that lone pair of electrons and make a double bond. Now what's the formal charge on that oxygen? 0. And what's the formal charge on the sulfur? +1. So we're moving in the right direction, right? So we've got a similar situation here where we've got a negative here and a positive there. We can fix that by taking one of these lone pairs and making it a double bond. So we'll take a lone pair out and create a bonding pair. And then the oxygen has its 2 bonds. And so it would leave with 6. It brought 6, 0 formal charge, and the sulfur also 0 formal charge. So we got all 0 formal charges. Sulfur has an expanded octet here. It has 2, 4, 6, 8, 10, 12 electrons instead of 8. But sulfur can do that because it has a 3D subshell available for those extra electrons to go into. Period 2 elements never have expanded octets. They'd have to bump people up to the next floor, and that's not going to happen. It's like, the people go into a hotel for a wedding, and you reserve some rooms, and you've got the floor, right? Maybe connecting doors even, and you don't want to send somebody up to a different floor because then you can't hang out together. I just made that one up. Never used that one before. Write a Lewis structure for xenon tetrafluoride. We'll put Xe in the middle and put fluorines around. And then we have to look at, well, how many valence electrons? Well, xenon has 8. And we've got 4 nitrogens, and they each have 7. 4 times 7 is 28, and 8 is 36. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Wait a minute. 32? I have to stick 4 more electrons in there. This is like, we've come up short before, but now we've got extras. Who's the big boy that can handle the extra electrons? Xenon. So we put the 2 extra pairs of electrons on the xenon, and it's got an expanded octet, and that's going to be fine. Do the formal charges, they're all 0. Let's look at H3PO4. This one's real similar to sulfuric acid. So we've got phosphorus in the middle and the 4 oxygens around it, and then the hydrogens are going to be on those oxygens. 3 hydrogens, phosphorus, and 4 oxygens. 24, 27, 32? Somebody do that. Did I do that right? Five and 3 is 8. 8 and 24 is 32. Okay. Get nervous when I get up here. Try to do math in my head. 2, 4, 6, 8, 10, 12, 14. 16, 18, 20, 22, 24, 26, 28, 30, 32. Looks good. Just enough. Check the formal charges. This has a -1 formal charge because it brought 6 electrons and it would leave with 7. This has a +1 because it brought 5 and it's going to leave with 4. So what we want to do is we want to take a pair of electrons from the oxygen that has too many and share them with the phosphorus that doesn't have enough for a zero formal charge. Doceri desktop issue. Reconnect. Reconnect. Okay. I did draw this once, but I'll try to do it again. Man. Okay. Double bonds shouldn't be so hard. There we go. By expanding the octet on phosphorus, we get lower formal charges. They can all be zero. And this is not just some game that we're playing with letters and dots. This actually matches up with what is observed structurally of these actual compounds. There is a double bond with that oxygen. Yes, question? Noble gases will want to have, well, they could bond. I don't know that they could do 8 bonds, but right, they already have a full octet, and so that's why they don't react very much. But they can be made to react, and when they do, they can expand their octets. They kind of have to expand their octets because it's already an octet by itself.